Hello guys, welcome again to this channel. Today we are looking into a very interesting series. We have two of them. They are very similar, and for the left one we have a finite series from 0 to n, and for the right hand side we have even an infinite series. And the question for the right series is, what is the limit depending on q? Q is a real number, could even be a complex number, and we are asking ourselves, what is the limit, in which cases we have a limit, and in which cases the sum is even infinity. And before starting with the actual topics, a short note: for q bigger or equal than 1, we know that the limit of this infinite series is infinity. This is because an infinite series can only converge if the sequence inside is a sequence that converges against 0. If you want to see a proof of this fact, and this is also a very important fact, please comment down below and I will provide you a video about this, a proof, an explanation as soon as I can. And without further ado, let's start with the actual topics. Actually, the goal is for this series to derive a formula. So this is very useful. We have finite terms here on the left hand side, and on the right hand side we know that the sum of this finite terms is exactly this number. So it's easy to calculate the right hand side, right? So especially for big n's, you can just refer to this right hand side and determine the sum. Okay, so we are doing this by induction, and as usual we are looking into the base case first, where n is 0. And if n is 0, both sides are just 1. Yeah, so you have just one term here, taking the power of 0, and q to the power of 0 is always 0. So for the sake of this video, let's exclude 0 here. So I don't want to bother with 0 to the power of 0 here, but yeah, the sum is 1 on both sides for every real number besides 0. So for the induction case, again we assume the statement is true for some natural number, so for some fixed natural number. So we assume the sum from 0 to m of q to the power of k equals 1 minus q to the power of m plus 1 over 1 over q for some fixed natural number m. So then we would like to prove that the statement is also true, so the formula is also true for m plus 1. So let's look at the sum from k to m plus 1. And here we can, as usual for induction proofs involving sums, we can split it up. So we just have the sum from 0 to m of q to the power of k, and then as we removed one term here on the right hand side, we have to add it separately, and the term we removed here is q to the power of m plus 1. Here on both sides we have exactly the same terms. And now that we have the sum from k equals to 0 to m, as in our assumption, we can apply the assumption, meaning we can apply the formula exactly on the left, on the first term here, so that we get 1 minus q to the power of m plus 1 over 1 minus q, and now plus, this term is still there, so we have plus q to the power of m plus 1. And now just we need to further simplify the terms, so we have 1 minus q to the power of m plus 1 over 1 minus q plus q to the power of m plus 1 times 1 minus q over 1 minus q, just extending by 1 minus q. So we have the same denominator on both terms. This equals 1 minus q to the power of m plus 1 plus q to the power of m plus 1 minus q to the power of m plus 2 over 1 minus q. You can already see that we have here the same term, minus q to the power of m plus 1 and plus q to the power of m plus 1, so they cancel out, which leaves us with 1 minus q to the power of m plus 2 over 1 minus q. And now we are actually done, because we started with the statement for m plus 1, because we have the sum from k equals to 0 up to m plus 1, and we are ending up with the formula for m plus 1, because here on the right hand side of our formula we have already m plus 1 involved, and we increase it by 1, so we have m plus 2. This is the formula for m plus 1, which means our induction proof is already done here. We achieved something very useful. We know that this formula is true, so the sum from 0 to n for q to the power of k equals exactly 1 minus q to the power of n plus 1 over 1 minus q. This is always true. You can always apply it to any series of that kind for any real number q. So let's start our consideration by writing down the limit where n tends to infinity of this series here. So by writing down the limit here first, this expression as a whole is exactly the one here on the right hand side on the top. But we can now apply our formula, meaning we have the limit where n tends to infinity of this expression here, 1 minus q to the power of n plus 1 over 1 minus q. So let's study this expression, and we can actually exclude the following case where the absolute value of q is bigger or equal than 1, because at the beginning I already told you a series only converges if the sequence inside the sum, this term here, is a sequence that converges against 0. So for those cases, the sum starting from 0 to infinity of q to the power of k is always infinity. So we are left out with the case absolute value of q is smaller than 1. So here we can apply the well-known fact that for a number with an absolute value smaller than 1, we know in fact that it tends to 0 if n tends to infinity, if we are taking this number to the power of n, like we have it here in this case. So this tends to 0, even for complex numbers. So this whole formula, this whole term here on the top, becomes now limit n to infinity of this series from 0 to infinity, q to the power of k equals 1 over 1 minus q. So we have an exact formula for the limit of the series, meaning it not only converges, but we actually know the value. This is something which is very rare. For a lot of series out there, we don't know the limit. Maybe we know that it converges, so there is actually some number as a limit. For this series, for this important series, we actually know for all the situations the limit, and it's 1 over 1 minus q. So just an example on how useful this can be. Let's consider the series k from 0 to infinity of 1 over 2 to the power of k. And we can just apply the formula. So we already know it's converging because 1 over 2 is smaller than 1, so this applies. And we know the limit because we can just apply the formula here, and this gives us 1 over 1 minus 1 over 2, which is just 1. So we know, this is very interesting, we know for this sequence it converges, again it converges, but we know the limit, it's 1. We can apply it to a lot of different situations and circumstances. I hope this was useful to you. If yes, please help this channel growing by subscribing to the channel, like the video, comment, and stay tuned for the next videos. Thank you.